Good morning, all of you. One more hot good morning. We have finished the part 1 syllabus of our second PU with complete detailings of electricity and magnetism. Now comes our second part. In the second part, we begin with the concept of modern physics, the dual nature of matter. Now, matter can be in two ways. The very existence of nature, the manifestation of nature, we will see either particle or the wave. These are two different entities of manifestations of nature. Now, by the end of 19th century or beginning of 20th century, it is established that light is both particle and as well as light is wave. We cannot decide whether light is particle or light is wave. It is decided by the light itself. That is why it is said to be light is dual in nature. This is the famous quantum theory by Max Planck, which is in the latter stage generalized by Einstein. Now, let us first take up the concept of quantum theory or those important facts according to Max Planck. The first one is photon. Now when we say photon, the question comes, we know that photon has energy packet and all, you remember all, you forget about all these things. Photon, it has momentum. Photon has momentum and momentum is a characteristic of particle. Then photon has the characteristic of frequency and frequency is the characteristic of wave. Therefore, now you can say that photon is a kind of blend of both particle and as well as wave. It has both the characteristics, momentum and frequency, such that now we just mention about 3 to 4 simple concepts. Remember, I can here go on doing equation 1, formula number 2, 10, so on. But I just give you only two important concepts. These two concepts will be the basis for all the examples based on the photons. So before getting into dual nature of matter, first let us understand the dual concept of light. That is what is radiation that we are talking about. Let us see some important 2 to 3 expressions, the concepts. First one is I said momentum. Momentum of photon. Momentum of photon P is equal to H upon lambda. H upon lambda. This H is the Planck's constant. The value is 6.67 into 10 rise minus 34 joule second. The smallest value known to the humans. So this H is, yes, this is a universal constant to be remembered, not given all the time. For the substitution, you should be knowing the value. At least 1 decimal I am telling you 6.6 at least times 10 rise minus 34. Now look at that unit, joule second, same as angular momentum. So Planck's constant has the same units as that of angular momentum. Now what is this lambda refers to? Lambda refers to the wavelength. Earlier as we are told, photon has this wave characteristic of frequency and how this frequency and wavelength are related. Therefore this lambda is equal to C upon F. C, the speed of light, and the F, the frequency term. Therefore, this what I meant F by C. F by C, H by lambda, lambda by C. Now, this is about the momentum. Remember the value of C, 3 into 10 rise, 8 meter per second. This is momentum. Next comes the energy of a photon. The basis for the entire unit in our second year, part 2, dual nature photons. The biggest formula is E is equal to H times F. Again the same Planck's constant and F, the frequency of photon. Frequency of photon given by, see here, F equal to C by lambda like that. And now here, this is Hc by lambda. Hc by lambda, because this is C by lambda term, right? Now here what we do is that generally here when it comes to the question of photons, the energy is too small that joule is not a appropriate unit. Therefore when it comes to the question of photon, most probably, that I can say 99.9% energy always expressed in the convenient units of electron volt, which is the smallest unit of energy. Therefore here, when you substitute the H value, C value and lambda value in SI units, you will get this value in, of course, joules. HC by lambda, it will be in units of joule. Whereas, remember, when we have the joule and the joule is to be converted into the smallest unit of energy, that is electron volt, it is divided with charge of electron, that is 1 by E times Hc upon lambda. Hc upon lambda. Now this H universal constant, C a universal constant and electronic charge is also universal constant. Substituting all those values and writing one approximation, one estimated value, we will write it as E is equal to 12,400 upon lambda is the expression. This expression we will use for all our CET NEET examinations, always, most of the times. And now here also two things are important. 12,400 by lambda, the units as I have told you in electron volt provided, I have, because already all those multiples and submultiples are taken here, lambda we have to substitute in angstroms. Supposing it is said as lambda is equal to 300 nanometer, generally it means that 300 into 10 raised minus 9 meter. Lambda we don't substitute that 300 into 10 power minus 9. 300 nanometer means 3000 angstrom. 3000 into 10 raised minus 10. All you have taken that minus 10 in this. Therefore, if I say lambda is equal to 300 nanometer, this is nothing but 3000 angstrom, one more zero for angstrom 10 power minus 10. Therefore, now here substitution 12,400 by 3000. No submultiple again 10 power minus 10 to be used. Already we have taken that. So, whenever you are using this expression, remember lambda to be used in angstrom without that 10 rise minus 10. So, this is in joules and this is in electrons. And what will be your CET NEET examples? For a given energy, finding lambda, or finding a lambda for a given energy or frequency terms, energy terms. So, this is what is the energy of photon and momentum of photon. See, here when we know momentum and energy, two more things I would just like to add, and don't take it as a kind of list of formulae. Number of times I keep on repeating this, because we have already the concept of forces and energies extensively according to our first PU syllabus. See, now what are the two more simple examples that I would like to make it out. First one is, suppose I have a radiation source of radiation, and power is given, power of the source, or sometimes also another familiar term is intensity of the source, the power of the source, intensity of the source. Power in the units of watt, intensity in the units of watt per meter square. Remember what do we mean by power? Energy per unit time. What is intensity? Power per unit area, and therefore it is watt per meter square. Units are very important. Watt per meter square, and this power is always in watts. Now P, the power of the source. Power of the source. Supposing it is said that. How? HF, the energy of each photons, supposing it produces n photons per unit time, and take it as n by t. N by t, number of photons in a given time interval. So P is equal to energy of each photon times n by t. This n by t is now what is written as Rate of emission. Is that okay? Important expression. Important expression. This is rate of emission of photons. Keywords. Rate of emission of photons by a given source. Rate of emission N by P, you will have it as P by HF. So that is P by H, and this F equal to C by lambda, right? P lambda upon HC, the rate of emission. Important expression. Here once again, N by T, one term, rate of emission. Lambda is one term, the wavelength, and P for the power of the source. Of course, H and C both happens to be universal constant. Three terms, two terms are given and third term is asked. NEET and CET. So difficult you see. Because people definitely never practice these concepts, and that is why they feel it a very simple example as most complex one. N by T, P and lambda are the three important things. Now comes. So let me make use of one more thing. Since I know the momentum of the photon and also I know this rate of emission, I will make use this for the case of force of radiation. Radiation force is one such simple concept I would like to discuss. Radiation force. What is why in this radiation force and all? Supposing I take a surface on which a radiation is incident, a radiation of frequency F or wavelength lambda incident. Even in that also, the simplest of the cases, normal incidence I am taking. If it is not normal incidence, if you get doubt, you can go through your hourglass notebook, and even then if you have any doubts, yes, you can contact me. Normal incidence, the simplest case I am taking. Now when radiation incidence on a surface, what happens? Three possibilities. Complete absorption of the radiation by the surface, or complete reflection of the radiation by the surface. Both natures what we call as black body nature, perfect black body nature. Total absorption, one possibility. Total reflection, the second possibility. The third possibility is either partial absorption, otherwise partial reflection. Now we are taking simplest of the cases. How? Normal incidence and total absorption. Let us take up this case. As I mentioned, these terms will have their regular meaning. Now what will be the initial momentum? Initial momentum Pi is equal to H upon lambda, which is directed downwards. Okay. Now what is final momentum? Since we are taking the case of total absorption, final momentum is 0, and therefore delta P is nothing but H upon lambda. H upon lambda. Whenever there is change of momentum, either in terms of magnitude or direction, rate of change of momentum gives rise to force. So that is what is the concept here, right? Therefore, what will be that force according to our Newton's second law, rate of change of momentum? This is delta P is equal to H by lambda for each photon we have taken. Supposing if the rate of emission is N by T, so what is the rate of change of momentum in per second? Then it will be this delta P times N by T. Delta P times N by T. Simple substitution. This is what is H upon lambda, and N by T, of course, already we have told P lambda by HC. P lambda by HC. So this is what we got as P by HC, capital F. Capital F is equal to P by HC. See, an important formula you can say. Again here, F for the force, P for power, and H and C both being constants. F versus P. Direct questions with substitution or asking for the relation between F and P as a graph, because here you will see Y proportional to X, a straight line graph you observe. So all such things you will find it. Now, supposing if it is said that, in this example, let us make a small change. If it is complete reflection means what happens? Earlier we said Pi equal to H by lambda downwards and Pf equal to 0. Now this time, complete reflection I will write. complete reflection, this is incident and this is reflected. Therefore, now you will find that P lambda is again h upon lambda, but vector reversing in the direction. Vector is reversed in direction. Therefore, now delta P becomes 2 times h by lambda. Therefore, the only change that we observe is that 2P by hc is the thing that we observe. So, power of the source, radiation source. One more thing, power of the source, rate of emission, and then wavelengths, momentums, keywords. Right? A practice of just 5 minutes will give you good number of solutions. Now let us see the next case with the photons concept. Radiation force. See, before I start one more topic, what happens in examination with students? Suppose I said force, but your question was like radiation pressure. Then definitely you start comparing that the topic is not dealt with in the classroom. But not the case, because we have told force, and what is pressure? Force per unit area becomes pressure. Right? You write down expression, earlier we said this force due to, it is P by hc we got, right? You remember? F is equal to P by hc. Therefore, now if this is what is radiation force, radiation pressure, F by A. Already have used capital P for power, small p for momentum. So here I simply write pressure, radiation pressure I will write. Radiation pressure, whatever symbol you want to use, you do that. Because P for pressure generally when used, already I am using it for power. F by A becomes P by A HC. This power by area, earlier what we have told as intensity, power per unit area, therefore it becomes I upon Hc. So this is what is radiation pressure. So every time, whenever we know some things, a small change can be there in our NEET or CET examinations, unlike board examination. So that is why your concepts are very important. Why I am taking so much of time even now, even before the CET examination, we are taking good quality time to make you understand about the concept. If it is from my side, I work for half an hour, at least it should be half an hour from your side also. Because generally I keep on telling you, you have to work or you have to spend double the time as done by the teacher for your better understanding. Now, this is what is about the concept of photons. Now let us come to the concept of the matter waves, the dual nature, which is proposed by de Broglie. Right? So de Broglie matter waves. It's a very interesting coinage of the term. Matter waves. See, the term itself is very disturbing one. Because matter and waves have exactly opposite nature. Now it is said to be matter wave. That is why it becomes so interesting. So this de Broglie wavelengths, let us not get into too much of details. I am giving you only some important concepts. When we say de Broglie waves, it is associated with all moving particles. All moving particles are associated with matter wave. So naturally stationary particles, no question of any wave. Likewise, follow the statements and take the merit of that. Conceptual question or numerical, you will easily solve it. All moving particles will have de Broglie wavelength such that whenever we say wave, wave has a characteristic like wavelength. Supposing if I have to say what is the wavelength of that wave, such that the wavelength is inversely proportional to momentum of photon is the principle, and such that here we write lambda is equal to h upon p. This is the wavelength of de Broglie wave. Remember, we have given the expression P is equal to h by lambda as momentum of photon, right? Though expression is the same, it is used with different contexts. Lambda is equal to h by p, lambda inversely proportional to 1 by p is an important relation. Now the point is that how many ways we can just change this h by p in the examination. Here I show one or two such cases. Again, don't take it for a list of formulae. So whatever we already know about these momentums or energies, we'll just make use and just rewrite this equation. How? Supposing if I write this as lambda is equal to h by mass times velocity. Mass times velocity. This is one concept. Next. Supposing not momentum or velocity, it is given in terms of energy. Then we have that famous expression, even a couple of weeks back also we have used momentum energy relation. So according to that, lambda is h upon momentum is under root 2 m k. K for kinetic energy. K is equal to p square by 2m, popular result, right? So h upon under root 2m k. Now follow each of the terms. This is what were big, very difficult NEET or CT examples. Here, lambda versus p, comparisons, inverse relation. The lambda versus velocities, again inverse relation, and depending upon mass also for a given momentum. Lambda independent of mass for a given velocity. Lambda proportional to 1 by m. So this should be your observation. What are the LHS terms and what are the RHS terms? What are the variables? How they are related? Now here similarly, lambda versus energy, you will see again inverse relation, but with a square root for both mass and as well as kinetic energy. So this is how. Let us solve afterwards few examples where I will make use of this, and in quick time I will do. How that ratio I am writing, you should get that. One more time, this lambda equal to 2mk, right? K for kinetic energy. Now again 2 or 3 other cases I am just showing you. And in all such cases, remember, we are making use of our knowledge of part 1 syllabus in second year, or part 1 or part 2 syllabus in first PU. These are the concepts. Now I am taking the case of charged particle. Supposing I am talking about keywords de Broglie wavelength of charged particle with energy. And supposing, now let us take up a special case of that. How a charged particle acquires kinetic energy? Again the principle of electrostatics. When a charged particle is accelerated through an electric field, a potential difference, it acquires kinetic energy such that charged particle accelerated through electric field. Accelerate through electric field, we write E is equal to, or K, the kinetic energy is equal to charge times potential difference. Here capital V for potential difference. Here also one V is there. This is for velocity. Therefore, the expression will take lambda is equal to h upon under root 2 m. This K we will now write V for potential difference and Q for charge. See one more time. LHS and RHS, how you observe the things. Lambda now depending upon mass of the charged particle, yes, inverse relation with square root, potential difference through which it is accelerated, inversely proportional with square root, depending upon a charge, inverse relation with square root. This is how you take these values. Now here, for your simple or for short answer, for short time answers in CET or NEET examination, I am taking the most popular particles. What are those? Suppose it is that electron accelerated through a potential difference, proton accelerated through a potential difference, alpha particle accelerated through a potential difference. In such cases, I am just substituting all these values because masses and charges, this value of h all substituted. You can make a direct answer out of that I would like to show here. Now for this expression for electron is under root 150 by capital V, root 150 numerator, denominator is capital V, and answer is directly in angstroms. Angstroms. Suppose I said V, this root 150 also would like to give you the number, it is 12.2526 upon root V angstroms. See? So simply V value is given, accelerated through 100 volts, 300 volts, 200 volts, substituting the values and getting. Suppose if it is said that V is equal to 100 volts, then it becomes 10, root under root 100 becomes 10, 12.26 by 10 becomes 1.226, and the answer is directly angstroms, that is 1.226 into 10 raised minus 10 meters, or else answer will be 1.226 angstroms. So every time when there are numerical values, identifying the right option with unit is very, very important. We are giving every time that important stress on the units, do remember. Lambda for electron, we have made a root 150 by V, supposing if it is proton. For proton also I am giving you this number, then this number instead of this I am writing the proton, it is 0.286 up to third decimal I am writing, or even if it is 2 decimals also it's okay. 0.27 you can take, okay? 0.27, 2 decimals I am writing. 0.27 by under root V, this is also in angstroms. And supposing if it is given for alpha particle, if it is given for alpha particle, see instead of proton, if I am taking as alpha particle. Alpha particle, small change in the numbers because mass and charges are different for different particles I am mentioning, it is 0.101 upon root V angstrom. So this root V is a common term that you have taken in all the cases. For electron it is, numerator is 12.26. For proton you have seen it as 0.286, and for alpha particle it is 0.101. Try to write it and try to memorize. Even if it is not the case, don't worry. If you don't remember also, in the examination, substitute the values, you will find your options very friendly. Now, as I have told you, every time whenever you write an equation, what are the different possibilities? Writing ratios, percentage changes, graphical representations, so on. Right? Supposing here I said comparison of lambda for two different particles, or for the same particle with the different potential differences, everything. So lambda 1 by lambda 2, all the results you are getting inverse and square root. Therefore I am writing a square root under which I am writing it as m2 by m1 q2 by q1, and this is v2 by v1. Remember I am writing capital V for voltage through which the particles are accelerated. Now it can be case of 1, 2, 3, 4 ratios are there. Any 3 ratios given and asked for the fourth one, or particle not changed, then this m2 by m1, q2 by q1, that ratios will be the same, like that. A very popular, difficult example from de Broglie wavelengths. Practice this and you will find good answers. To show you one more simple example and making use of our known concept here. Earlier we have taken charged particle accelerated through potential difference acquiring kinetic energy. That is substituted in our de Broglie wave equation. Now, supposing if it is a neutral particles and they acquire kinetic energy because of thermal agitation. So the keywords are chargeless particles, such as it can be either molecule of a gas, or it can also be said as thermal neutron. For such cases, how they acquire kinetic energy? It is because of thermal agitation. Now for such neutral particles under thermal agitation, what will be the equation for de Broglie wave? Because all moving particles are associated with wave. If now here our expression was lambda is equal to h upon p, I have shown you this, h upon under root 2m k, m for mass of the particle and k for the kinetic energy. Supposing now I take the case of gas molecule. I take the case of gas molecule, then it becomes lambda. For that case, K, let us write the kinetic energy. K, the kinetic energy of gas molecule, we know that law of equipartition of energy, according to which it is 3 times of half small k capital T. This capital K for kinetic energy I am writing, this is small k for Boltzmann constant. 1.38 into 10 raised minus 23 joule per Kelvin. This K value 1.38 into 10 raised minus 24 joule per Kelvin, Boltzmann constant, and this capital T for absolute temperature, because we said thermal agitation. This capital T for absolute temperature of that gas under which the molecules are in the random motion. Therefore, K is equal to, I will write it as 3 times half kT per degree of freedom. Gas molecule 3 degrees of freedom multiplied with 3. So 3 by 2 kT. If I substitute, what will be the expression we get? Lambda is h upon, let me write here, right. This is lambda is equal to h upon under root. This becomes 3 by 2 kT, 2 kT cancel. We write it as 3 m small k capital T. Please do remember this capital K for energy I am writing, this K for Boltzmann constant. So lambda equal to h upon under root 3 m kT. Now here most of the times gas molecule, when you are given, instead of asking for calculation, the important result is that lambda proportional to 1 upon root T is the important conclusion that we take, and this is how questions will be asked. For the given wavelength, what should be the temperature? For changes of temperature, what will be the changes in wavelengths, etc. That is how. This is lambda 2 by lambda 1 if I am writing. Again, many times I have told you, one more time repeating, 2, when I said 2 and 1, this terminology, final values, unknown values, I write it as 2. 1 refers to the given values, the initial values, known values. So lambda 2 upon lambda 1 is equal to under root T1 by T2 temperatures in absolute scale. And this is again, remember, symbol and unit, capital T to be taken in absolute scale, given in centigrade plus 273, and then substitute after getting also. Supposing I got it as T2 is equal to 1200 Kelvin, if I got the equation. Again, finding the right option is important. A, B, C, D options are given. The number, first option itself is given as 1200, but given in degree centigrade. But generally oversight or over exactment, or maybe a kind of negligence for some student, they look at the number and they don't look at this unit, and it will be, that is how mistakes are more and more. As I have told you, be harmonious in the examination hall as much as possible. When it is the question of numbers, please be careful about the unit. Look at it, the final expression, right? So 1200 Kelvin, the answer is minus 273. If you do it, it will becomes like 927 degrees centigrade it becomes, right? 1200 Kelvin becomes 927 degree centigrade it becomes, like that. So absolute temperatures is an important caution I am telling you here. This is for gaseous molecule that you have taken for which 3 degrees of freedom. Supposing if it is said as thermal neutron again acquiring energy because of thermal agitation, and there is no question of the 3 by 2 term, therefore here it will be 2 mkt only, or no 2 also, yes 2 get cancelled, you get only mkt, here m for this, now I am writing for neutron, Baba, thermal neutron, the 2 term gets cancelled, so the mkt you will get again the same result, lambda proportional to 1 by root T, whether it is thermal neutron or the case of thermal gas molecule, the expression this one is the same, lambda proportional to 1 upon root T. Whereas I would like to tell you this, if supposing asked in the examination for neutron, substituting the values of m and k, I am doing it and giving you as a number. If you can remember, it will be helpful for you. Just try, not any must. If you can try and remember, it will be good. Then for thermal neutron, this lambda value is nearly 30.03 upon root T. And the answer is directly angstroms. So for a given temperature, what will be the de Broglie variant of neutron? Substitution and finding the answer in angstroms. And as I have told you, if you need to remember all these things, the quality of your practice and preparation will decide whether it gives you stress or it gives you a confidence. And I always wish you be with your right practice to improve your confidence and stamina. Do follow the number of sessions given by all your teachers. Don't forget to practice your assignments and feel liberty in calling your teachers and clarifying your doubts. Have a great day.